So, good evening, Balkan. We have some really interesting stuff coming up for you now. But first, let me ask you something. Who here among you likes to eat ham? And who here amongst you is a ham? So, ladies and gentlemen, here is Travis Goodspeed with his talk on polyglots in amateur radio. Enjoy.
Howdy do. I'd like to begin with a quick public service announcement. The cat that is going around the museum, I've named Goga, after the Turbo Folk superstar. I expect all of you to call her Goga while giving her little pieces of food so that she answers to that for the years to come. So today we're going to be talking about two protocols in particular that are popular on amateur radio. One of them is PSK31, and the other is RTTY, or RTTY. I've been playing with these protocols in a way that is not entirely legal by amateur radio rules, but is close enough. So a lot of what I'm teaching you how to do would become illegal if you just added cryptography to it or secured it in any way, because cryptography is illegal on amateur radio. But hypothetically, if you had to, say, smuggle books into a country that didn't allow books, like let's say you wanted to send a book to Germany, and the Germans don't allow books that describe how to write exploits, right? So you have like the uncensored edition of the Bug Hunter's Handbook, and you want to send that to Germany, but you don't want to physically go, you want to send it by ham radio. In this lecture, I'll be showing you how to hide extra information inside of a legitimate amateur radio message through steganography. I will also be showing you how to create polyglots that are valid as multiple digital formats at the same time. For example, I can combine PSK31 and Morse code in order to have a message that's valid in both formats, so that the machine can easily read the PSK31 and the human being can interpret the Morse code. Now, we're talking about radios here, but internally, you should think of the receiver as a parser. You have a software program on the receiving computer that is interpreting the data that comes through the air in the same way that you would interpret a file format. So a lot of the tricks that you do with a file format will also work here. And these tricks are not that hard to find. Of particular importance is something called a parser differential. This is a fancy way of saying that two receivers have a different view of the same message. One of the most useful things for a parser differential is in breaking SSL. If you can create a certificate that looks as if it represents one domain to the browser and a different domain to the certificate authority, then you can sometimes trick the certificate authority into signing something that it really shouldn't. The same thing happens in radio. So there was a project that Sergey Bratis and I did a few years back called Packet and Packet, where we managed to smuggle in an entire radio packet from layer 7 to the physical layer by a parsing bug on the receiver combined with natural noise. This allows us to email a Wi-Fi beacon and have it drop out as the message is being transferred. You can even do this so that not one single byte of the interior message is visible to the naked eye inside of the exterior message, by making a packet that's meaning changes when it's shifted by 1/8 of one nibble, or 1/2 of one bit. So Sergey and I began coming up with ways to perform this on amateur radio protocols. And our goal is not quite steganography, in that we're not trying to hide information, although we can, Instead, we're just trying to figure out all of the crazy things that can be done with these protocols. If in the future it becomes necessary to sneak information, you have my blessing to use these techniques in that way. So what we're trying to do here is we're trying to create a single message that contains both the bear, which is like the public view of the message, and also the books, which is a hidden interior view of it. Sort of like Russian Matryoshka doll. So in order to get to this, I'm going to briefly explain how modulation works and which pieces of modulation you can begin to abuse. First, each receiver is designed for a particular modulation type, and it ignores anything that's of an orthogonal type. So, for example, if you have an FM receiver, the FM receiver will generally ignore the amplitude of the transmission. So you can do minor changes in amplitude without distorting the audio or without anyone noticing. So in our case, we have the signal being modulated on top of the radio carrier wave. If we change the, yeah, there we go. If we change the strength of the signal, the actual amplitude, we get AM modulation. And if instead we change the frequency, then we get FM modulation. There's also phase modulation. This diagram is a little bit of a lie to children, and I'll get to why in a later slide. But the gist is that you can encode a bit by changing the phase of the sine wave. So you're jumping back and forth between sine and cosine. And what the receiver does is it multiplies the current signal by a time-delayed version of the signal. And if the phase has changed, it becomes positive, and if it has not changed, it remains negative. Now, when you're viewing this on a receiver, you generally look at what's called a waterfall. And inside of the waterfall, the signal sort of spreads around its center. Now, a mathematician thinks of this in whatever fancy mathematical form. From an amateur perspective, it's more of an intuitive or a traditional view. There's what's called upper sideband, which is where the radio frequency is just downshifted to become audio. And this is what most of the digital forms of amateur radio use in shortwave, in international communications. And this is particularly cool because you can work with all of your digital encoding as a modem written in software working on a wave file. And your radio appears to your computer as an extra sound card over USB. Whatever you play to that sound card gets transmitted, and whatever comes in from the radio comes in through that sound interface. So that all of the programming that you have to do, you're doing on audio files. And when you get it wrong, you can hear where you got it wrong and why. This makes developing it a lot easier than writing software-defined radio code. And you don't need any fancy libraries. You can implement all of this yourself in Python without having to rely on GNU Radio or other fancy techniques. The general two styles used by ham radio for these modes are frequency shift keying. In frequency shift keying, you just have a high frequency that's a 1 and a low frequency that's a 0, and you jump between them to send your message. On the waterfall, this looks like two lines, and the data is in which tone is being used at that time. On the air, these are two different radio frequencies, but when you downshift it, you hear them as two different audio frequencies, and that audio contains all of the information. So you implement your modem in the audio spectrum instead of at the much higher frequencies that are used on the radio. This is also a low data rate, because in amateur radio there isn't much space to go around. All of the shortwave frequencies combined are about 30 megahertz wide, which is the same as a high-end Wi-Fi card. So the entire world has as much bandwidth as your Wi-Fi card has. And in order to properly share it, small segments are allocated to each user or each style. So for amateur radio, we don't have very much bandwidth. And in order to make up for that, we send very narrow signals. So narrow that you can actually have multiple signals inside of the audio band at once. So you can hear multiple people talking, and your modem can decode all of these and follow the conversation. We also use what's called single sideband. The upper diagram here is a traditional AM signal. The AM signal you can recognize because there's this central peak, and then you have two side lobes that come off of it. And the side lobes have the same information. So you can either listen to the left one or the right one, and the full information is there. This is wasteful. So instead, amateurs send only the upper half, which is called upper sideband, or they'll send only the lower half, which is called lower sideband, and this allows them to use half the bandwidth. This is sort of like a solution to this man-spreading moral panic that the United States is going through these days. In our situation, we have Alice and Bob who are trying to have a conversation, and Eve is trying to learn what that conversation is really about. And Eve is doing this by passive eavesdropping, so she's not faking any signals, she's just recording everything and then reading through all of the traffic. So one way that Alice and Bob might communicate is with RTTY. This is a protocol from the 1940s that was used by military teletypewriters. It uses 2 FSK modulation, and it's Baudot-coded, so there are 5 bits per letter. And this is the same technology that the serial port standard was originally developed for. So you can describe this as 5N2, in that there are 5 data bits, no parity, and 2 stop bits per character. In the same way that your dial-up modem might have been configured as 8N1. This is a picture of what the teletypewriter would look like. And in order to shorten your transmission, you would actually type out your message into this paper tape on the right, and then replay the paper tape in order to send your message across the air quickly. A modern operator console for this is done in software. This is a program called FLDigi that allows you to control your amateur radio, and also it acts as a soft modem in order to convert your conversation. So the operator will type in his message here in this text. The number at the top left is the frequency that the radio is tuned to, which is not the frequency that the message is tuned to. The message is at the radio frequency plus the audio frequency. So if this is at 14.070 megahertz, and you're transmitting at 1 kilohertz audio, the actual data signal will be centered at 14.071. And this is what it looks like on the spectrum. The left red line with the yellow surrounding it, that's the 0 bits. And the right are the 1 bits. And this sort of scrolls upwards. So time is the y-axis and frequency is the x-axis. Operators would send ASCII art through this, or Baudot art. This is a picture of Seattle Slew, the horse that won the Kentucky Derby in 1974. Now the alphabet used by this is not ASCII. To make things more efficient, they left out support for things like case and letters. So all of these messages are in uppercase. You'll also note that each 5-bit code can be either a letter or it can be a number. And the way that this is implemented is that there are actually 2 signals called figs and letters. If you send figs, it switches to the figures alphabet so that you can send numbers and such. And if you send letters, then it lets you type in letters. So then the Russians wanted to use this technology. So transliterated rather than an actual Russian. Let's say that you want to order 4 vodkas. Right? The first thing you learn in Russian class, 4 vodka, пожалуйста. So you have your 4 vodkas as letters. If you change to the figures alphabet, it's exclamation mark 974 space semicolon and so on. The Russians wanted to be able to send across the Cyrillic alphabet. So they took advantage of the null character. And on a Russian RTTY implementation, sending a null switches to a 3rd alphabet and allows you to send Cyrillic. The Cyrillic alphabet here is in the Latin alphabet order, so that if your radio does not support the Cyrillic alphabet, it will transliterate it to Latin and you'll still be able to read the message. And then your bear gets his vodka. The letters command, though, is also used as an idle tone. Because in addition to recording your message and then transmitting it, you can also operate live, in which the machine waits for you to type the next letter. If you type more slowly than the computer is transmitting, it will send this sequence of all ones. And the reason why it does this is that 0 bits get put around it for the stop bits, and that allows the timing to be synchronized on the receiver. You can also alternate the idle tone. So a normal transmitter will always have just letters as the idle. But if you do letters and then figures and then letters, no one on a computer will notice. On a physical teletypewriter, there will be this constant kerchunking as it's switching between the alphabets. But unless someone is monitoring you with equipment from the 1940s, they won't notice this change, and thus you can include extra bits during the idle portions of your conversation. So this way, your bears can run through the village, and they can keep some books on their backs. You can do similar things in PSK31, which is the 1990s replacement for RTTY. Those of you who saw the ham radio station in the yard today, there's a little box on top of the radio that had a serial cable and some audio cables running to it. That was a PSK31 adapter. PSK31 uses 31.25 symbols per second. And the reason why it uses this rate is that this is about the speed that you can comfortably type at without feeling rushed. So you type a little bit faster than the machine is sending, and then you use the absolute minimum amount of bandwidth so you can have as many conversations in a single audio channel as possible. This only takes 60 hertz of bandwidth. This is actually less than the channel separation that's needed for Morse code. Whereas before we had 2 different lines on the spectrum graph, this yellow line here, in PSK31 we only have one vertical line. And again, the actual frequency is the sum of the audio frequency and the tuned frequency of the radio. So we're transmitting our carrier at 14,071 kilohertz. PSK31 inverts its phase to mark as 0, and there's no phase inversion to mark a 1. So on this top sine wave, you see that the sine wave is going along, and then right in the middle, it abruptly reverses direction. It sort of works like that. In practice, the volume has to be dropped to 0 at the moment of the transition. If you don't do this, then you get harmonics throughout the band, and it physically hurts your ears, because as the speaker is wobbling outward, it abruptly gets yanked back by its magnet, and that creates like a popping noise. In software, you implement this by switching between sine and cosine. In hardware, you can implement this by turning a delay on and off. And the phase is not inverted to mark a 1. So a 1 in PSK31 is just a sine wave. This figure is a little bit hard to see, but the amplitude of the greater wave gets dropped down to 0 at the moment of the transition. This is done to prevent the harmonics. So the way that the receiver decodes this, if you remember that a positive value times a positive value is always a positive value, and a negative value times a negative value is also always a positive value, you can multiply the signal with its delayed self so that the result is only positive when the phase has changed. Otherwise, the value will always be negative, and the result of this transformation is a line that's squiggling along beneath the 0 line and only jumps above it when a 0 bit is encountered. Similar to RTTY, PSK31 has a varicode alphabet. The reason why it does this is that ASCII is not very efficient for English text because it assumes that every letter has to be the same width. So in PSK31, kind of like Morse code, your symbols, your letters are different sizes. Lowercase letters are shorter than uppercase letters. Common letters are shorter than rare letters. There's a table that you can look up. Inside of this table, you'll see that the letter E is just 2 ones. A space is a single one. And you'll also see that the uppercase letter E is a lot longer than the lowercase letter E. So if you hit the caps lock key on your transmitter, your message will begin transmitting more slowly because each letter is significantly longer than it would be in lowercase. There are other rules here. I'm going to jump back to the table as I read these. The first rule is that every letter begins and ends with a 1. So in all of these that are shown here, as well as the rest of the larger alphabet, every single letter begins with a 1 and ends with a 1. The other rule is that no letter contains more than a single 0 in a row. So none of these have more than a single 0 before the next one. The third rule is that letters are separated by 2 zeros. So what the receiver does is whenever it sees 2 zeros, it takes the buffer of whatever came before those 2 zeros, and it looks that up in the symbol table, and that's where the letter comes from. So there are tricks that you can do with this. The first trick is that you're required to have at least 2 zeros between letters, but you could have a lot more than that. You could have 3, you could have 4, you could have 500, you could have 5,000. So what you can do is you can send 3 zeros in between letters to mark a 1 and 4 zeros between letters to mark a 0, and use that to encode 1 extra bit per letter in order to hide a secondary message. And the receivers will ignore all of this. The other thing about PSK31 is that illegally long letters are always ignored. The author of the PSK31 standard is British, and he wanted to send the Great British Pound symbol. But the Great British Pound symbol is not in ASCII, and it was not in the original alphabet that he constructed. So the way that he added that was he just made extra letters that were longer than all of the old ones, and he defined those to the upper half of the ASCII table. But if you go further than that, it remains undefined. And the receiver has to be error tolerant because there are lots of errors on the radio. So whenever it comes up with something that's not in its list of valid characters, it ignores it. So you can sort of like flip the standard around and send your entire message as one illegally long character, which will roll off the end of the receive buffer. And as long as you never send 2 zeros in a row, it never tries to look that up. And at the very end, when you do send 2 zeros in a row, it finds something that's not in its list and it skips over and keeps moving with the rest of the message. And in this way, you can hide extra information. There are also physical tricks that you can do. Once again, PSK31 is generated as audio. Here you have a laptop on the left and a ham radio on the right, and it's just 2 audio cables running into the back of the radio. So I implemented PSK31 in Python. And this is something that you can do in a weekend with the proper documentation. And you don't need any fancy libraries or anything like that. You begin with your audio rate. So PSK31 was designed for digital signal processors that did 8,000 samples per second. I'm doing it at 48,000 samples per second just to give it greater precision. So inside of your audio file, every 48,000 samples are 1 second of time. There's also a volume. I want the volume to jump up to half of the 16-bit sample size. The other thing that I want is a divisor to choose what audio frequency I'm generating my tone at. In this case, I just divide my audio rate by 1,000, which will give me a 1 kilohertz tone, sort of centering my audio signal where the radio can best handle it. And then the length of each symbol is the audio rate divided by 31.25. This is how long a single bit is. I then have like a throwaway variable I, which is my index within the sample. And that's from 0 to the length of each symbol. And I have a value for each one that I produce. And a phase, which is 0 for sine or 1 for cosine. Now, if you naively implement this and you just abruptly switch from sine to cosine, it sounds absolutely horrible. I would play it for you here, except that the speakers would break and everybody would get very mad at me. And tomorrow you would have to listen to the speakers trying to yell over the crowd without amplification. So what you do instead is you use what's called a root-raised cosine filter. What this does is it drops, this is the program Audacity opening a wave file that my tool has produced. And wherever you see the amplitude drop down to nothing, that's where the phase shift is actually occurring. This width here is actually 1 bit. Wherever you see it drop, that's a 0 bit. And wherever it does not drop, that's a 1 bit. The difference in spectrum, you see how the one on the left is nice and smooth and narrowband, and the one on the right is just sort of shitting over the entire audio space? The one on the left is filtered, and the one on the right is not filtered. So real PSK31 filters only the bits that change phase. And there's no filter when the phase remains constant. So one thing that you can do is you can do PSK31 envelope ambiguity, which is where you drop the phase even at times when you don't need to. And what the receiver is looking for is any time in which the phase was dropped in a 1, and that gives you 1 extra bit of information per 1 bit that you're transmitting. The zeros don't contain extra bits because they have to be dropped. And most receivers won't notice the difference at all. So when you're receiving this on a laptop and you're tuned to the right region, it sounds very similar and it looks identical, and the computer throws away all of the differences. So in this case, the message on the top is the classic PSK31 transmission. The one at the bottom has been modified to drop the volume in each of the 1 bits. And a proper PSK31 receiver hears no difference between these. By doing this selectively for individual bits, you can hide information. The other thing that you can do is you can realize that the PSK31 is tolerant of very, very wide swings in amplitude. If I'm transmitting with 100 watts and someone down the street is transmitting with 5 watts, both signals will get through. So what you can do is you can change the amplitude of your transmission at each point in time that you're dropping down to nothing. So you can use this in order to hide Morse code in your transmission. I'm going to play 2 audio samples for you now. This first one is a PSK31 transmission containing a lecture that I wrote on how to implement PSK31. that little wobble that you hear, that's when the amplitude is being dropped. And that's normal PSK31. There's nothing fancy about that. There's nothing special about that. This is my ham radio call sign in Morse code and also in PSK31. So as a human operator who knows Morse code, you can hear the call sign in it. And some of the dashes in this transmission, one in each of the letters, also contains that letter as PSK31, so that your receiver can identify the call sign automatically as well as by audio. This is what the spectrum looks like. This is the spectrum of the letter K, which is da-da-da. And the first da, the one at the top, contains the PSK31 version of the letter K. This is the same letter drawn out in Audacity. And you can see that it's the one on the left that contains 0 bits. So the first da contains the letter K as PSK31, and then the rest just contain nothing. They're there for filler. You can also do a PSK31 RTTY polyglot. RTTY cares about relative power. So you're transmitting either on the high frequency or on the low frequency. And what matters as far as the receiver is concerned is which one is stronger. PSK31 doesn't really care which one is stronger. It only cares about the phase. So we can combine the two. We can have the low frequency contain one PSK31 transmission. The high frequency can contain a different PSK31 transmission. And we can jump the strength of each to make one stronger for a little bit and the other stronger for more time. And this creates a signal that's valid in both protocols at the same time. It's a polyglot. There are also some versions of PSK31 that contain error correction. So because it has forward error correction, some of the bits on the air can be flipped without damaging the message. So what you do is you flip them intentionally, knowing that they will be corrected on the other side, and whether the bit is correct or incorrect hides your extra secret information. There's a DEF CON presentation last year in which this was implemented for JT65, which is a related ham radio protocol. JT65 is a particularly good target for this technique because it has a ton of error correction. The protocol was originally designed for reflecting a message off of a meteor as it's falling through the atmosphere, and then catching it on the other side. And this is very unreliable, so they had to put in lots of error correction in order to sneak the message through despite the damage. Now, this technique is also like, a little bit fragile in theory, but in practice, even though the tools should be very easy to write to identify this, they haven't been written. So what would be useful to do as a project would be to take the audio recordings that Drapeau and Dukes published last year at DEF CON and write a tool that runs through and identifies whether the damage to them is intentional or accidental. As in, like, is it an honest mistake that the bit came out wrong, or was it intentionally transmitted as wrong? Which you can do when you have a good signal-to-noise ratio. So there's one last trick that I want to share with you. How many of you have Ethernet networks at home? Okay. And you know that, like, Wi-Fi, someone can sort of hear how much traffic you're using, even though they can't necessarily know what you're sending across when it's encrypted. So Madeline is a way to do that for wired Ethernet. So data runs over the Ethernet, and we're going to suppose that the attacker can control some of that data, but not very well. So let's say that you're running HTTP, and you're running it over Tor, and I want to identify where in Novi Sad you are, and I know that you're in Novi Sad, but I don't know anything more than that. What I can do is I make a message in Morse code. It's like the client is here, right? And controlling the hidden service on Tor, I start sending that message as Morse code in terms of how much bandwidth you're using. So if I want to send a DIT, I use a lot of bandwidth for a very short period of time. If I want to send a DA, I use it for a longer period of time. So how many of you wired your own home Ethernet yourself? Okay. So you know how you've got the twisted pairs and you put the little cap on them? And you know how you're supposed to untwist them just before you plug it into the cap? And you know how it's so much easier if you give it like 5 or 6 centimeters of unwinding? And you know how China makes such awesome, cheap network switches these days? And you can just buy a cheap network switch and throw it in? So this is the letter K transmitted from what used to be my home Ethernet network before I rewired it to amateur radio. This actually came out at 28.121 megahertz. And I was able to hear this from an antenna on my roof. I then called a friend of mine who lives down the street, and he was able to copy a Morse code message that I sent him just through bandwidth usage. And the reason why is that when you untwist those twisted pairs, they leak just a little bit of radio data. And when you have that combined with a cheap wireless router, it leaks a little bit more. And this signal is something that you can pick up with a radio receiver if you find the right frequency. So if you hunt around and find the right frequency, you're then able to receive this information that's exfiltrated out. So the next part of this project is that I want to do a wireless capture the flag project. I'm going to be transmitting on 20 meters from Philadelphia. And this transmission will hit most of the Western Hemisphere. If you have a proper antenna, you will be able to receive it here in Novi Sad. It's by upper sideband, so you either need an amateur radio receiver or a high-end shortwave receiver. You don't need a transmitter. And what I'll be doing is I'll be transmitting test messages that contain hidden information as a sort of capture the flag. So you can take an audio recording of it and then try and mess with it in order to figure out what the hidden message is. And each one of these transmissions is a little bit different. The other thing that I'll be releasing this afternoon on GitHub is the tool that I've been using to produce the PSK31 samples. This is in a few pages of Python. It's rather easy to read, and you'll be able to use this to generate your own tricky PSK31 transmissions in order to hide extra information. I'll also be publishing lectures on PSK31 in PSK31 that you can receive with the radio, along with the capture the flag transmissions. And the source code to these lectures is included with the PSK31 tool. In conclusion, I'd like to remind you that the digital protocols on the air can be messed with in the same way that file formats can. That the receiving radios are parsers, and in the same way that you can find bugs in parsers on a PC, or in software, or in a phone, you can also find bugs in the coder-decoder chips. You can find bugs in the protocol itself, or ambiguities that allow you to hide extra information, or to send a message that can only be received by certain software. And this is a great way to get started in actually writing radio software yourself with less of a learning curve than software-defined radio would take. When you start playing with software-defined radio at the beginning, it's great and it's very easy to get lots of results. And then you sort of hit a brick wall where everything becomes impossibly hard and unrelated to what was before. I think that this can serve as a sort of stepping stone to work with radio techniques, but in the audio domain, where bugs are easier to find, and you're able to catch up and to fill in the signal processing knowledge that will later allow you to write software-defined radio from scratch and without relying so heavily on pre-built libraries. Thank you kindly for your time and attention. I think I have time for a question or two. No questions? Cool. Thank you kindly. I'll see you around.